Hello, my name is Devlin, and today I'm going to be showing you my culminating presentation on the photoelectric effect. Now, before we start, can I get a quick show of hands? Who here thinks that they know how many subatomic particles there are? Anyone? Yes, you there. 3? Nope. But you're close. It's actually 53 as shown right here. Now, I'm going to be starting off my presentation with my question and my rationale. Then I'm going to move into my explanation of the photoelectric effect. Then I'm going to give the current uses and the possible future uses of the effect. And then I'm going to wrap it up with my conclusion and my works cited. My question is, what are the current uses for the photoelectric effect and how can they be improved? Now, I chose this topic because I have an interest in physics, especially the subatomic and astronomical side of things, the quantum physics and the astrophysics. I decided to go with the tiny particles, the quantum physics. I've also always wondered how solar panels work, so that was a big plus, figuring out how they work. And this also does not fit in with modern physics, which I will explain later. Next slide. Now, what is the photoelectric effect? The photoelectric effect is where light shines onto a metal, and the metal releases electrons. The amount of electrons released is based on the frequency of the light, because as the frequency of the light increases and the wavelength of the light decreases, the amount of photons released from light also increases, and photons are tiny particles, and all of them each carry an equal amount of light. As a particle hits an electron, the electron absorbs the photon, takes its kinetic energy, and is launched out of the atom. These electrons can be collected to create energy. Now, the speed of the photon is increased by the intensity, not the amount. As the intensity increases, as the brightness of this light would increase, the speed of the photons being released from it would increase, but not the amount of them. So this would, it has to pass a certain point, which is called the work function. This is the amount of intensity that must be reached for the photons to have enough kinetic energy to release an electron from the atom, metallic atom. Most would perceive it backwards, and this is why it does not fit in with modern physics, as modern physics would say that the amount of photons released would be based on the intensity and not the frequency, but it's the other way around. What are some of the current uses of the photoelectric effect? There are solar panels, light detectors, and light amplifiers. Solar panels have many tiny little photoelectric cells inside of them. These cells consist of 3 things: a glass envelope, an anode, and a cathode. And I will go more into detail about this on the next slide. There are also light detectors, which shoot out a constant beam, which is reflected off of something, and then that beam hits a metal, which releases electrons off of the other side. And this activates something. I'll go more into depth on the next slides. And there are also light amplifiers, which take light and through the photoelectric effect, they turn them into electrons, which are then multiplied and turned back into photons, which will increase the brightness and the contrast of an image. An example of that would be night vision goggles, and an example of a light detector would be an automatic sink or an automatic door. This is a photoelectric cell. It consists of a glass envelope or a little glass bulb that is vacuum sealed. There is no air inside of it. It is airtight. There is a cathode, which is a bent metal plate. Light shines onto this cathode, and this cathode reflects electrons off of the side that the light is hitting it. These electrons then hit the anode, which is a thin metal rod that collects the electrons and turns them into energy down here. This is how a light detector would work, specifically an automatic sink. This is a little black box that you would see, but under the sink. This is releasing a constant beam. It's invisible. It's usually an infrared beam, which is being reflected off something and hitting a receiver. This receiver is a metal plate which releases electrons off of the other side as the beam hits it, and these electrons are sensed by an electric circuit telling it that nothing is in the way, that the beam is on and hitting the metal. If something blocks the way, it's going to stop hitting the receiver. The receiver is going to stop releasing electrons, and this is going to tell the electric circuit that something is in the way, and it should activate whatever it is, whatever it is meant to activate, like a sink in this case, or an automatic door. This is an example of a light amplifier, specifically night vision goggles. It takes light from a normal, unenhanced, dark image. It takes the photons from that image, hits them against a photocathode. This is a plate, this is a metal plate. It releases electrons off of the other side, and these electrons are passed through a microchannel plate. That multiplies the amount of electrons. These electrons then hit a phosphor screen, which is electrically charged and releases photons off of the other side, which causes a brighter, more contrasted image to be created. Some of the possible future applications of the photoelectric effect. It can be used for a free electron laser, which is a laser that actually breaks the photoelectric effect. It takes light at extraordinarily low frequencies with super large wavelengths and extraordinarily high intensities. So the photons being released from the light are going extraordinarily fast. And they have so much kinetic energy, the few photons that are being released, that they don't hit the electrons and are absorbed by the electrons, but they actually pass through multiple electrons at a time and can knock out waves of electrons for just one photon. It can also be used to increase the efficiency of solar panels by using more electrically charged metals, heavier metals, that have more electrons in them and can last longer. They can also be, the cathodes can be shaped differently to have more of the electrons actually hit the anode. It can also be used for quantum computing, for tiny systems that require micro amounts of power. It can use the photoelectric effect, a photoelectric cell, to collect light energy and turn this into energy for a microcomputer to help with quantum processing. In conclusion, the photoelectric effect denies the light wave theory. This is a theory that light is released in waves, not in particles that are called photons, which is denied by the photoelectric effect. It also defies previous thoughts about photons, saying in modern physics it would say that photons would be released more as the intensity increases and the speed of them would increase as the frequency increases. But it is backwards, it's the other way around as proven by the effect. And it takes a lot of manipulation to break. The free electron laser is actually able to break the photoelectric effect, but it takes a lot of manipulation. The photoelectric effect stands true for a very long time. And I guess you could say that the photoelectric effect has a bright future. Here are my works cited. Here are my photos cited. Any questions?